please remember to turn off your mic during the presentation. Without further delays, I please to hand over the mic to Dr. Eleni. Dr. Eleni, the virtual stage is yours. Enjoying the session, everyone.
Thank you for the very nice introduction, Zero, if I pronounce your name right.
Yeah.
And, also, I know my surname is also quite different with you, but I'm happy that I'm able to join you virtually. So today I'm going to present you, as you mentioned, some research topics that we're working on lately regarding the fire safety challenges of complex buildings. So this is, as already mentioned, after a short introduction, we will discuss some fire safety challenges associated with the design, ventilation conditions, smart components that can be integrated in buildings, evacuation methodologies of first responders. Then we will proceed in presenting limitations and challenges, and we will conclude with some comments and also highlight how important education is in our field. So actually, as you can see, it's a rather holistic view of what are the fire safety challenges. And as you can see on the title, we have the word complex. So complex buildings. I struggle to group together various components that make difficult to understand or explain some concepts when it comes to buildings. So I found that the word complex building can be a suitable one, because according to some dictionaries, one of the definition of complex is not easy to understand or explain, actually not simply. So when it comes to buildings, what is complex? So for example, here you see a facade of a building that certainly is not something that you can say it is considered as simple. So when it comes to building, complexity can come from different components, such as design, height, facade, the use of the building itself, and the use of the materials. Now, why do we have those types of buildings emerging? And why is this coming a trend nowadays? Actually, you must be aware that there is a green agenda promoted in most of the countries. And fire engineers should approach net zero challenges. So actually, some people might say, actually, one of the issues that we should do is actually balance safety and sustainability. So this is a very nice graph showing which countries have made to carbon neutral pledge. So actually, more than 130 countries have committed to carbon neutrality, and this is a goal. So the goal now is to reach net zero until, as you can see, the target year is 2030, 35, 40, 45, 50, and beyond. Actually, only 2 countries have achieved net zero by now, and most of the countries around the world are committed to achieve net zero by 2050. So this is also reflected in most of the regulations in most of the countries. So these are some of the documents that are issued from the European Union, the British government, and the Australian government, just as an example. And we see here that reduction of energy consumption is a strategic goal to most of the countries in order to ensure sustainability and reduction of greenhouse emissions. And actually, this is the reasons that regulations are getting stricter and stricter when it comes to thermal properties and design of construction and buildings. So this is reflected on how we design our buildings. So what is the rationale of the design that we have until now? So we need to achieve aesthetics because we need to like buildings that we live in, but at the same time, now it's a priority that we design energy efficient buildings, sustainable ones, and that includes innovative components. But let's not forget that one of the main issues is to have safe buildings. Sometimes, though, balancing environmental goals and fire safety can be a rather complex procedure. So, when it comes to building fire safety, there are multiple layers that can ensure this safety of buildings. So actually here we can see a very nice illustration from the Modern Building Alliance, illustrating the 7 layers of fire safety in buildings. Actually, this is a good point here to highlight that one of the main disasters is fire. So according to the Modern Building Alliance, the first layer is prevention, then we should ensure detection and early suppression, and then we should make sure that evacuation and compartmentation are well designed, and we should have structural safety, and then obviously this building safety should also be reflected to firefighting techniques. So I try to follow this schematic and illustrate some of the components of our research regarding those layers of fire safety in buildings. Now, fire. According to the United Nations Office for Disaster Risk Reduction, this is the definition of a disaster. So according to them, a serious disruption of the functionality of a community or a society at any scale due to hazardous events interacting with conditions of exposure, vulnerability, and capacity, leading to one or more of the following: human, material, economic, and environmental losses and impacts. So this is exactly why fire is a major disaster. So this, one of the goals of the Sendai framework for disaster risk reduction is to achieve minimum losses due to such reductions. And actually this year, 2023, we are exactly at the midpoint of the target, which is 2030. So what are the consequences of fire? First of all, we have loss of fire and life and injuries. There is a huge health impact through smoke exposure to people and also to firefighters. Property and infrastructure losses, business interruption, ecosystem degradation and soil erosion, and huge firefighting costs. When it comes to statistics, actually, these are some as illustrated by the Fire Safe Europe. So in the past 2 decades, we had a total of 86.4 million fire incidents that had caused more than 1 million fire deaths. And this corresponds to a total annual loss from global fire hazard at a range of 1% of the world GDP, which is approximately $857.9 billion. So on an average, we have 3.8 million fires, caused 44,300 fire deaths every year in both the developed and developing countries across the globe. So these are serious hazards. And actually, if you see also in the brochure attached here, we have more than 5,000 fire incidents each day only in the European Union. So we need to follow 3 steps in order to build a fire safety future. And this is to collect data, to share best practices, and to set a vision for fire safety in buildings. So what is the aim today? So in trying to define what is a complex buildings, I would like to start from high-rise buildings. So as you can see here, these are some examples of high-rise buildings around the world. High-rise buildings play an increasingly important role in contemporary architecture, and because they have rise from a necessity to process population growth and its concentration in cities, as well to cover high demand in the city centers. So actually, at the left-hand side, we see the Marina Towers in the USA, which is an example of one of the first high-rise buildings built in 1963. What is interesting about this building is the geometry of it, and also it includes a physical plant penthouse. Now, at the middle, we see the Bahrain World Trade Center, which is built in 2008. It is a 240-meter height building with 50 floors, and actually, it is the first high-rise building in the world to have integrated wind turbines into its design. So, as you can see at the middle of the building here, we have 3 wind turbines producing energy. So actually, this is one of the components of smart cities. Can we put energy producing elements inside our buildings? Now, the third building on the right, is one of the latest buildings built in Shanghai, China, in 2017. It's obviously it's almost twice the height of the Bahrain World Trade Center. It's approximately 492 meters high, and as you can see, the design is not a simple one. But a second category of complex buildings is actually buildings that have curvilinear design. Curvilinearity is a concept that has been widely used for many years from many architects, and actually it was inspired by some of the most famous ones, such as Gaudi or Zaha Hadid, and the style is has been propelled into the forefront of the architectural consciousness. Now, on the right-hand side, we see one of the most complex curvilinear buildings, which is a museum of the future, built in Dubai in 2022. And actually, this is a building that aims at a platinum LEED rating in terms of green rating. So it's not only a complex and fancy building, but it is also a green building. Now, here you see some other examples of curvilinear designs and how they can incorporate it into the design of buildings. So if we focus a little bit on this component, let's try and define what is curvilinear. So actually, Esser is one of my favorite artists. So this is one of his famous lithographs back from 1935, the Handen with reflecting sphere. So continuous curvilinear surfaces, such as the one that we see here, have been featured prominently in architecture and especially in free-form buildings. And now, curvilinear surfaces can offer lightweight, but also sturdy structural forms that are aesthetically pleasing, but also can make efficiently use of space. So this is these are some of the reasons that architects might prefer those shapes. What do we see here? So here we can actually see a curvilinear surface. So here we see a diagram of a curved surface, which is divided in different pieces. So, Actually, this is the way that we define curvilinearity. So we use normal vectors. So normal is a vector vertical to a surface in order to define where is the orientation of the surface and what are the geometrical features of it. So what is our was the aim of our research recently was to check what is the effect of curvilinearity on building design, and especially focusing on facade. But let's start with what is a facade. So a facade is actually the skin of the building. It keeps it separated from the external environment. And now, as we did mention, there is a trend of green building concepts and sustainable construction. So actually, energy efficiency of the facade is one of the major drivers in construction industry. Now, in order to promote those types of design, we have the development of new energy efficient lightweight materials with good thermal insulation properties, and they are used to reduce the heat gain and loss through the facade. Also, as you know very well in Queensland University, other sustainable materials such as wood can be used as part of facades. Now, the problem is that we still have a big number of facade fires that are happening around the world. So what is the reason? The reason is that though we have put a lot of our attention into building those types of green, efficient, and smart facades, there is less attention to the behavior of such facades in case of a fire. So actually, new facade fires have often resulted in significant changes to the behavior and the role of facades in the fire spread of buildings. But also we do have new techniques, new materials that are developed, and actually they also contribute, and we don't still have a full understanding of how they contribute to facade flame spread. Some might argue that non-combustible materials is a guaranteed solution. I would highly disagree on that, because still you might have flame spread and you still might have problems. So actually, the issue is not to ban specific materials, but rather to learn how each material can contribute to fire and engineer appropriately. So here, for example, you see some facade fires that happened recently. I mean, obviously you should know, and you should have heard of Grenfell Tower event that actually triggered a lot of debate into this research area and really pushed the direction of the research on how we should understand facade fires in high-rise buildings. So here is the Torre del Moro fire apartment building in Italy, 2021, and Taksim Yardım Hospital in Istanbul, 2018. I do present those ones because they're not only facade fires, but they are facade fires in high-rise buildings with curvilinear geometries. So we have established that facade can be a critical element in building fire spread. Nevertheless, we should make clear that flame spread is a very important mechanism. And you see here, I found this image fantastic. This is an image from the image competition. I think it was from the IFSS. And this is from the PhD of Gorner back in 2012, that we can see how orientation and geometry actually influence flame spread. So you see how vertical orientation, such as the one that we can see in facade fires, can influence how the flame will be attached near the surface. And also we see how differences in the orientation can influence the way flames will spread. And actually, this is not a new field. A lot of work has been done in the past, and it has been acknowledged that flame spread on building elements, especially on walls, is an important application area for basic flame spread theory and the materials properties obtained from tests. So, for example, the work of Quintier, as displayed in many of his work, such as the principles of fire behavior, is a pioneer in the field. And also, there are many different researchers that have focused on those types of fires. Currently, there are some practical approaches and there are some analytical methods to predict correlations between the theories of ignition, flame spread, combustion, and the material properties. But still, we have an occurrence of many incidents around the world. So our student Anoop really tried and record those facade fire incidents. So building on the database that was initially produced by Matthew in Hayes lab in Imperial, he did extend the data and he did include recent fires. And actually he recorded what are the different types of buildings. So as you can see here, 75% of those buildings are rectilinear buildings. That means this is orthogonal, they are orthogonal buildings, but 25 of them are curvilinear and 18% of those are non-orthogonal. So this is a registry until 2022, if I'm not wrong. So that includes all the information as depicted in media regarding high-rise building fires. So actually, as part of his PhD, we're trying to understand what is the effect of curvilinearity on how facades evolve in curvilinear geometries. And the thing is that this is a study that has started many, many years ago. So one of the first researchers that did start investigating external venting flames, denoted as EVF throughout this presentation, was Yokoi back in Japan, and he investigated the physical characteristics along with Webster and Seigel in the 70s. Now, after that point, Margaret Lowe, 1978, started investigating the formation and validation of a set of correlation to predict compartment fire dynamics and the effect of facade fires on the heating of external structural elements. This work was further progressed by Oleszkiewicz, Omija, and Klopovic. Actually, Klopovic did the first large-scale test of experiments in Canada back in 1999, and she did investigate the full-scale study of the phenomena associated with realistic fire load burning and what would be actually the effect of the ventilation, which is another research area for us. And then onwards from 2000, there are plenty of researchers focusing on that. So some of those research results have already been fed to some of the codes around the world, such as the Eurocode 1. And these are used in day-to-day engineering design. So usually in order to investigate the fire behavior, there are plenty of different tools that can be used, such as the use of nominal fires, time equivalence methods, and in compartment fires, there are specific methodologies for the facade fires. And then on top of that, we can use some more advanced models, such as zone or safety modeling. So in that terms, there are two approaches in the design. So firstly, we have the prescriptive approach that nominal fires are used to generate thermal loads. And this approach indicates a set of rules for the design and verification of the structural elements. Though one of the main drawbacks and restrictions is that most of the prescriptive approaches currently available can be applied to rectangular geometries with restricted floor areas, no ceiling openings, and no specific thermal properties for multi-layer facades or more complex facade components. Now, an alternative to that is the performance-based approach, where more advanced models such as CFD or zone modeling can be used. Now, the issue here is that no particular guidance is given, and the identification of the means lies to the engineer. So these are the two different approaches. Now, as part of the performance-based approach, in order to investigate what is the effect of curvilinearity, a set of numerical simulation has been designed. So actually, these are the different set. This is a table illustrating the different set of simulations in order to investigate what is the effect, first of all, of the geometry. So two geometries have been investigated. One with a curvilinear profile, which is depicted here as geometry 1, and one with a rectilinear one with an equivalent volume. So the dimensions as depicted here are the same. So we have the same width and the same length. So, but each time the height is different in order to make sure that we have the same volume in our calculations. Now, the second parameter is the effect of ventilation. So two different ventilation conditions have been used. So first of all, we have the forced draft conditions where two openings exist at the sides of the geometries, and then there is another ventilation condition where only one opening is located at the fire compartment. Then the third parameter that is investigated is the effect of the heat release rate of the fire. So if we take a glance of the numerical results, we can see that actually, yes, so at the left-hand side, we actually see the flow development and the heat release rate and the flames ejecting from just one opening in a curvilinear configuration. So this is geometry number 1. On the right-hand side, we see the same 4 megawatt fire under forced draft conditions. So we can see that here, zooming in, we see the formation of recirculation zones that are actually pushing and driving the externally venting flames towards the exterior. And we see the recirculation the recirculation zone formed inside the compartment for the no forced draft condition here. But when we have two openings, we have the formation inside the formation of two recirculation zones at the interior of the fire compartment. The maximum velocity is 9.5 meters per second, and we can observe that the flames are tilting towards the outside the exterior of the building. Now, this is a completely different behavior, and also this is illustrated here. So what we see here is the velocity field at 500 seconds after the beginning of the simulations for a 4 megawatt fire located at the geometrical center of the room. Now, on the left-hand side, we have orthogonal geometries, rectilinear one, whereas on the right-hand side, we can see the curved surfaces. And we can see on the left, on the top side, the no forced draft condition, so only one opening here, whereas on the lower part, we see the forced draft condition where we have two openings. So in curvilinear geometries, so we did choose 500 seconds to actually represent fully developed fire conditions. So in compartments with curvilinear geometries, as we can see from the right-hand side images, We have observed a smoke movement that can be a complex fire dynamic process because we have the interaction of turbulence, combustion, and radiation with the geometry of the compartment. A clear recirculation zone is observed in the no force draft condition at the upper hand side, but this is not observed in the force draft conditions. And researchers have studied in the past how smoke flow is developed in curvilinear tunnels, for example, and they have observed how various curvatures can affect smoke movement, but not many people have focused on how externally venting flames would be formed in case of curvilinear geometries. Now, when it comes to the temperature field, this is a contour of the temperature at the middle of the compartments, both for no force draft and force draft conditions under rectilinear and curvilinear geometries. What we can observe is that the stratification of the fluid flow of the smoke at the interior of the curvilinear geometries is different compared to the rectilinear ones. And actually, though the shape of the flame usually fluctuates, we can see that the externally vented flame plume size are increased in curvilinear geometries for all heat release rates. So this is also depicted here. So this is a contour of the intermittency profiles of the flames at the center line of the compartments for both the geometries. And what we can see here is that the externally venting flame plumes generated under curvilinear fire compartments have more intense, have higher heights and are more intense. Now, the plan is to actually progress this research and perform fire testing to validate the results and actually investigate what is the effect of the scale. So this week, Anoop and his team are finalizing fire testing in this curvilinear medium scale structure. And then the plan is to progress testing and use this facility that exists in the International College of Engineering and Management in Oman. And preliminary work has been performed in order to assess how these fires will evolve, but also the plan is to test the different ventilation conditions in large scale to also investigate the effect of scale. Also, the geometry of the opening is of great importance. So different type of openings will be tested in order to understand what is the effect of curvilinearity in openings. Now, one of the other parameters that are very crucial when it comes to development of a fire is the interaction of the draft, that means the ventilation conditions. So as part of the work that we have performed with the Technical University of Ostrava, with Jan Smolka and Kamila Kepna, and the International College of Engineering and Management in Oman, and VUBP, we have investigated what is the effect of no force draft and force draft conditions in the development of the facade fire. So there are fire safety engineering design methodologies for the prediction of the dimensions of facade fires, centerline temperature, and the heat flux, and generally the impact at the facade. But with the design of this experimental configuration in the University of Ostrava, we did try and investigate what is the effect of the ventilation under forced draft conditions. So what you see here, you see the front and the side view of the experimental apparatus. So this is a compartment fire with two openings at the front and the rear. And this whole configuration is placed underneath two hoods. Now, to investigate forced conditions, there is a fan placed at the rear side that is actually forcing air into this compartment under 2.9 meters per second. So in that case, the investigation focused on the effect of the opening dimensions and the wind speed under forced conditions. So on top of that, Anup, as part of his thesis, also numerically investigated the same configuration in order to validate its procedure and to help extend the findings of this research to investigate more and perform parametric analysis. So what we can see here, this is the experimental apparatus and this is the numerical setup. And here at the bottom, you can see the experimental setup, the burner, the two openings, the facades, and here the fan at a distance of 2.5 meters, forcing air through the openings. So as part of the work, a validation process was performed in order to investigate the validity of the predictions. The data plotted, as you can see here, showed that 70% of the predictions fall within the 30% error margin, indicating a good agreement. Now, when it comes to the investigation of the effect of the ventilation, this is a screenshot 150 seconds after the beginning of the fire, illustrating what is the flow field developed and the relevant flames when we have a forced draft of 2.9 meters per second. Here at this image at the top, we have the 20 by 20 centimeter opening, and here at the bottom we see the larger opening. At the left-hand side, we can see the no wind condition, so we have no fan there, and at the right-hand side, the forced conditions. Now, for all the opening sizes, bidirectional flow was observed as fresh air was entering through the bottom part of the opening, and hot gases exits through the upper part of the opening. Now, the externally blending flame is located closer to the adjacent facade, and under forced draft conditions, we see similar flows, inflow of air from the bottom part of the opening, formulating two recirculation zones. However, once the fan induces the presence of wind, the recirculation zones near the opening are no longer visible, and we have a single recirculation zone at the interior of the fire compartment. Now, one of the first tasks was to actually validate and compare the temperature profiles. So these are two graphs indicating how experimental results compares with numerical results for the different openings. So with the different colors, black, blue, and green, we see the different opening dimensions, and then with the dotted lines, we see the experimental results, and with non-dotted lines, we have the numerical results. Actually, there is good agreement, especially, and at the left-hand side, we see the no-wind condition, and at the right-hand side, we see the forced draft condition. We can see a very good agreement, but there is a slight disagreement at the larger opening heights. Now, the same results are plotted at the temperature profile at the facade. Now here we have still a good agreement, but in case of the greater opening during both forced, during no wind conditions, we see a bigger disagreement. Here we can see the developed thermal field in the same circumstances. So under no wind condition, under forced conditions, and here at the higher part is 20 by 20 centimeter opening and the 40 by 40 centimeter opening. So you can see how different the stratification of the flow is, how differently the venting flames are ejecting through the opening, and how actually the forced wind conditions can actually influence their shape. Now, when it comes to fire safety of challenges of smart cities, as we did already highlight, the climate change and the energy sources shortages that are due to fossil fuels drive the use of alternative renewable options in the construction industry. Now, there are plenty of renewable sources out there, and actually it is a fact that solar is the fastest growing technology worldwide. Along with their exploitation, safety issues and adequate management related to novel technologies are expected. So the rise of awareness of fire risk related to renewable energy technology, and with a particular emphasis on photovoltaic systems and energy storage system, because you don't only need to have photovoltaics to gather energy, but you need to store this energy somewhere. There is relatively low research that has been done until this point, and the relevant involved actors, such as the government authorities having jurisdiction and first responders organizations, should have access to new research data in this area. So we should make sure that actually smart cities are also safer cities. So we should focus on fire issues in smart cities and what is the impact of the use of the renewable technologies on the safety, and how photovoltaic and energy storage system can be protected, and how first responders should be supported. So this is a holistic approach that should be implemented. One of the most useful and important documents when it comes to the fire safety challenges of green buildings is the Fire Safety Challenges of Green Buildings and Attribute, a report published by NFPA by Brian Mitcham and Margaret McNamee back in 2020, illustrating some of the basic concepts that should be followed. Now, if we try to define a green building, according to the World Green Building Council, a green building is a building that in its design, construction, or operation can reduce or eliminate negative impacts and can create positive impacts on our climate and natural environment. Green buildings preserve precious natural resources and improve our quality of life. So in my opinion, these are the buildings that should be designed from now on. When it comes to resilience, what is resilience? Resilience is the ability to prepare and plan for, absorb, recover, and more successfully adapt to adverse event. Such an adverse event can be fire. So we don't only have to have green building, but we have to make sure that we also have resilient buildings. So resilient buildings are those which are designed for long life, and this should be our target. Resilience can be achieved in many ways, from the use of durable and high reliable components to ease of repair and renovation to high level of resistance to expected hazard impacts. And attributes can include reduced susceptibility to single points of failure, increased robustness, redundancy and reliability of systems and components, and flexibility and adaptability. So actually, the target is to achieve sustainability. There are many definitions of what is sustainable or what is sustainability, but it can be defined as responsibly interacting with the planet to maintain natural resources and avoid jeopardizing the ability for future generations to meet their needs. And a very good technique is to use the risk tetrahedron framework as indicated by Brian Mitcham and Margaret McNamee. And this framework is illustrated here. So we see here the risk framework of united fire hazards associated with green attributes that is surrounded by three main themes, which is the societal objectives to actually create modern green buildings which do not endanger climate, attributes which express their societal objectives, and control mechanisms that are put in place to ensure that these buildings are communities and are fire safe. Now, when it comes to building integrated photovoltaics, and with a specific emphasis in facades, these are also mentioned as BIPVs. BIPVs plays a vital role in achieving net zero energy. And this refers to photovoltaic modules which can be integrated into the surfaces of the building and are placed can replace conventional building materials. Now, there are many reaction to fire classification tests that can be used for testing those facades, but there is no clear methodology of how those technologies can be treated when they are installed in facades. One of the preliminary works and very vital works that have been performed is the experimental study on flame spread under photovoltaic panels and also in photovoltaic panels under different orientation by Christensen, Frauji and Jomas back in Edinburgh. And that was part of Christensen's PhD. And they did investigate how flame spread could evolve under those systems. And that can actually fed to how traditional firefighting strategies can be upgraded in order to include those circumstances. So there are still many critical issues of fires involving photovoltaics, and they need to be addressed in all the emergency phases. And this is part of the work that we're currently doing at UCLan. Now, when it comes to photovoltaics and energy storage system and the methodologies for the first responders, there should be identification of the likely fire scenarios and effective fire protection measures, and then characterization of photovoltaics and energy storage systems and fire safety related variables. And then what is the connection of those systems with the owners and the emergency first responders, and what is the effective training tools for first responders. Now, this should all fed the resilient communication systems. And what is the purpose of a resilient communication system? To reduce first responders' intervention time, to act towards safer emergency operation and prevent fire propagation with mitigation actions. So, talking for effective fire evacuation, that was one of the main targets of our recent project funded by the Home Office, the SAFE project. So in that frame, the strategies aiming at effective fire evacuation in high-rise residential building project funded by the Home Office in the UK aims to establish the most effective methods of evacuating high-rise residential buildings. It focuses on how residents and firefighters, because we shouldn't forget that there is an interaction between them, should interact and make decisions about evacuating in a fire situation. After the Grenfell Tower, there was an inquiry that took place, and it recommended that the government should develop national guidelines to carry out partially or total evacuation of high-rise residential building. So back in 2019, December, A joint Home Office and Department of Leveling Up Housing and Communities Technical Steering Committee was set to support the research to support those recommendations. So the SAFE project is actually targeting on investigating how recommendation 33.22a can be implemented. So according to that recommendation, the government should develop national guidelines to carry out partial or total evacuation of high-rise residential building. And such guidelines can include the means of protection, fire exit routes, and procedures for evacuating persons who are unable to use the stairs in an emergency and who may require assistance. Those people are mentioned as people with vulnerabilities, and those can include disabled people, older people, and young children. Because let's not forget, we might have high-rise buildings, but those buildings are meant to be used by people, and all people should have equal opportunities and have easy access when it comes to evacuation. Now, this is the project team. James and Shepard are the PIs, and along with many people, we tried to investigate some of those concepts. So the aim of the research is to assess procedures and processes to establish the optimum operation response in the event of a high-rise residential building, and when should be a need for a move from the stay-put policy to full or partial evacuation, and make relevant recommendations. So there was both, there were two phases in this research, and the second one, the second phase included both physical testing and evacuation modeling. And the purpose is actually to understand how we can move from the stay put to a full or partial evacuation in the safest way possible. Now, the research questions that we tried to reply is the prevalence of evacuation alert system and the impact on the evacuation strategies, the existing strategies for evacuating single, dual, and multi-stair buildings, because this is also a very important factor when we design complex and high-rise buildings, how many staircases they are available for evacuation, and what are the most appropriate evacuation strategies when it comes to people with vulnerabilities. And egress consideration for occupants during evacuation. So back last May 2022, we performed a large-scale experiment along with the National Fire Chief Council and the London Fire Brigade. And we are now completing the data collection and analysis of those results. Now, the first phase of the project focused on the operational research on how to establish most effective methods. So a series of interviews and questionnaires took place. And today I'm going to present you some of the views of the occupants. So from an occupant point of view, the largest portion of the occupants were tenants, with 13% of them having small children and 2% having both children under 12 and elderly people in the same household. So most of the building had one or two staircases, while only 15% have more than 3 staircases. Now, 70% of the occupants live on floor lower than 10th floor, and 75% of them lived under the 6th floor, and 24% of them lived in higher floors. Now, the prevalence of evacuation alert system and the impact of strategies was one of the major concerns and one of the research questions that were addressed. And it was evidence that only 18% of the occupants were aware of the alert systems on their buildings. And actually, a majority of them considered that those were inadequate in the building they live in, including text messaging, visual alert system, and vibrating pagers, that only 2% had access to them. Now, 55% of the occupants said they were not aware of any neighbors with vulnerabilities, and some people identified the communication among neighbors in high-rise buildings as low. Now, one of the things is that none of those occupants were aware of any help or the support their vulnerable neighbors would need in case of an occurrence of fire. And there was a lot of criticism against the implementation of PIPs that was expressed by 27% of the occupants interviewed. Almost 80% considered that there was a lack of adequate information and there was not enough knowledge of the policies that should be followed. Now, when it comes to falling debris, which is a very important issue when it comes to high-rise buildings, overall, only 36% of the occupants interviewed were aware of the dangers associated with those falling debris, and almost 2/3 of the occupants considered that mitigating falling debris risk is an exclusive responsibility of the fire rescue services personnel, because most of the occupants are willing to evacuate without considering this. So actually we can see that the occupants' levels of awareness of falling debris was somewhat aware and moderated aware. And actually, most of those findings were fed to phase 2 testing, that we did test different evacuation strategies, and we collected human performance data for evacuees with and without vulnerabilities, and we did consider what would be the difference if we would have an evacuation alert system installed on the building or not. We did test in single and dual staircase buildings. This information will be published very soon under the reports that you see here. Now, what are the limitations and challenges? So there are many limitations and challenges arise from complex buildings, from open space architecture, especially now that we use high combustible nature. We have high combustible nature of control of room contents, and we have new construction materials. And also when it comes to firefighting, we have longer response times. And this, in cases of active fire protection, we have prescriptive codes that have limited guidelines on providing acceptable limits for functional and performance reliability of new and existing fire protection systems. And there is a lack of rational provisions to standardize the qualitative and quantitative requirements of fire protection systems, such as sprinklers, smoke detectors, fire extinguishers, etc. Due to those factors, most of the building codes and standards have significant differences in terms of active fire safety provisions in buildings. And when it comes to passive fire protection systems, the fire resistance is assessed under standard fire exposure at service load level, which is a simplified approach with restraints and simplified failure criteria. So it's important to also upgrade those. Now, what is the solution? In my mind, the solution is to implement an integrated framework, to implement strategies for improving fire safety in buildings, and that would require 4 different approaches for the fire protection of the features, then how regulations and enforcement should be informed, how we can provide awareness, and how we can cultivate common and civic sense, and then as a 4th component, how we can improve technology and firefighting resources. And actually, the aim would be to actually implement those strategies as early as possible into the design of the buildings, and actually fire risk of certain feature into the design can be fully assessed even before the construction begins, using BIM, for example. And of course, all these should be integrated into our education. So this is some work that we've performed with this project, the skill to be a fire expert, that provided an online learning platform for fire experts on various components. Now, what are the conclusions? I very much agree with what NFPA illustrates. And according to that, fire safety is actually a sustainable practice. And it's a sustainable practice that should be taken into account during, before, during, and after a fire event. And if we reduce the amount and severity of fires, we can reduce wasted materials, pollution, and save money through the life cycle of the buildings. And this is also highlighted in the roadmap for research as demonstrated by SFP. So here, this is an example of how we can adapt our data, innovative technologies, design methods, and approaches in order to tackle building fires and improve resilience and sustainability. And when it comes to safety, new materials, smart and complex building actually challenge how we use safety, and more research should be fed into the interaction of fire and structure when it comes to modeling, and more round-robin studies should be performed to have access to experimental data to validate our softwares and our codes. And we should pay more attention in identifying error margins and the need for guidance for proper use of numerical models. And all of that should feed standardization of design files and the relevant analysis approaches. Thank you so much. If you have any questions, I would be more than happy to discuss. Hope it took a little bit longer than expected.
Thank you very much, Dr. Elena. Yeah, if anyone have questions, just feel free to use chat function or just directly turn on your mic.
Cricket in the background.
I don't know if that's good or bad news, actually.
A bit of both. I will start off in case people need a bit more time to think. Thanks again, Eleni, for taking the time and for this very insightful presentation. It's really good to see an academic being able to tackle issues that are quite related to the industry, and this is what you're presenting is very tangible, and hopefully it will move in the right direction, not from your end, but from the end of the authorities and the EU, because we have facing the same issues here in Australia as well. I've got two questions, more like your opinion or view on those. First one is, what happens, what's your view, I guess, in buildings, in new buildings that, let's say those high rises in the CBD of a major capital city, let's say like Sydney or London, where you get an office building and you have, the building gets built, and then throughout the life of the building, there are changes in the building itself. So from the base build design, you have let's say 3 or 4 compartments joined together for one firm, and then another lawyer firm decides to purchase a couple of more floors, and they completely change the compartmentation of the building, and then that changes the evacuation strategy, which is very different to the overall strategy of the building. But then when the fire engineers are called in, they look at that little fit out section and not necessarily how this will impact the building holistically. Is there a plan, if you're aware, in terms of the authority side, is there a guideline that this needs to be tackled, or how this can be tackled in the life of a building?
I've discussed with many people regarding the effect of the change in the use of buildings because this is what we've discussed today, that we should tackle fire safety throughout the building's life. So changing the use and the modification should be taken into account. Now there are no specific guidelines to follow this, but this is high in the agenda at the moment, and it's being implemented, it takes some time, but it will be implemented in the guidelines because it's of great concern, especially in high-rise buildings and how they change. They're like an organism, so we should be adapted to that and make regular adjustment to the policies and the strategies implemented to each building. And actually, each strategy should be tailor-made to each building and not following generic approaches, as can also lead to many issues and problems.
Yeah. I mean,
very valid point, very valid point.
Because bespoke solutions are right, but sometimes it's at the mercy of the building owner or the developer if they're willing to go down that route. Because they want to keep the building occupied, they don't want to, let's say, upset other occupants or high-end occupants they have in the building. But yeah, I think that's really good. The other point I had, it was again related to high-rise buildings. There are buildings nowadays that they are being built in the cities and they're built above, train stations, spaces where they have to accommodate a huge influx of people going in and out, and different fire scenarios, like if there was a fire down at the platform where the trains are, how this would impact the building above, because the buildings are actually connected now. There's a connectivity, or a fire at the building above, how those people will be evacuated out. And like those train stations are built with a different mindset. Let's say they're supposed to accommodate the next amount of people based on a study by 2050 or whatnot, but then the commercial tower serves a different purpose. And sometimes it's really hard to get state government with the private owner to agree on the guidelines, because sometimes beyond the code, the operators, for example, the train operators, they have their own requirements that then you need to justify. So in a different life, not as a PhD student, but as a fire safety consultant, we had to deal with issues where we had to address non-conformances to the code because they were not in line with, they had to be in line with the guidelines of the operator, but they were not necessarily in line with the building code. So there's a bit of a gap between guidelines of operators in trains or tunnels versus what the government has actually put out, and there's a bit of a gap there. I don't know, what is this the case in the UK or in Europe more widely?
I would like to add something what you said. What about multi-hazard approaches?
Okay.
So what about fire after an earthquake at the same building? So these are issues that should be addressed in a more holistic, point of view. So we should treat each and every building as part of a grid. And, in that grid, we should try and identify not only the changes at the building, as you did mention at your previous question, but also the change in the lifetime. And also, what if something else will be built? And I don't know if you remember a fire that was due to a reflection from a car that was parked at the side of the high-rise building in London. That was many years ago. So there was a fire that was due to a reflection of the sun, of the sunlight at the car, and then that ignited some part of the facade. So actually, they had to change the orientation of some of the buildings. So actually, we need to be. We need to have a wide view of where the buildings are placed, And now I don't know how that can be implemented in a regulatory framework, because that's quite a complex approach. But this is where performance-based design can be very helpful, because you can, create a strategy which is tailor-made to your building, and you can take into account. So the problem in my mind is that there are no sufficient guidelines, not necessarily regulations, but guidelines as to how a design should be.
That's right.
So in that sense, you did highlight some very good points, and hopefully that can be implemented into guidelines and then later on to regulations.
Mm, mm. Yeah, because this is generally driven from regulations, in fear of regulations when you're a
Yeah, we
developer.
need that fear. If we don't have that, human nature is not very
Yeah.
even from other things than making sure people are safe. So the main drive when we do design fire strategies or our buildings in general is to make sure that people live comfortably inside and they are safe. Now, some people don't have this drive, and we should make sure that competency is something that, is very strictly defined, and people that will assess things and strategies are competent enough to do so and have the required knowledge that can help guarantee safety of people at any level.
Yeah, I wish many people share the same view when it comes into buildings. Thank you. That was great.
Thank you, Stavro.
I don't see anything online. Have you,
There is something on green roofs.
Zeroy? Oh, there you go.
So actually, vegetation, facades and roofs is one of the green attributes that is widely used. And now there is research done on that, and it's not that advanced at the moment, but we should focus more on trying and identify. I mean, we have some project going on at the minute with green facades and how fire is spread in those. And I'm aware of some large-scale experiments. Also, if I'm not wrong, Wojciech in Poland did some experiments lately on green facades. So hopefully we can have the results soon enough, and we can inform the relevant guidelines in different countries. Now, you say here different countries, so that's another point worth of discussing. We don't have unified approaches throughout all countries. So as you've seen with the net zero policies, each country has its own target. This is the same with the fire performance and the relevant regulations regarding fire. So in my mind, it would be super nice if we can get everyone on board and all should be up to date with the relevant research. Now, the problem is that when you participate in committees and when you have to review results, this is a lengthy procedure because everything should be double checked and cross-referenced. And this is the reason that it takes a long time. So the more people they would be engaged, the more, the faster can be, the faster the results can be implemented to practice. But that's a very good point, Weng-Xuan.
Actually, just another point on a friend of mine just reminded me. We are a profession that we are a bit more reactive than proactive when it comes to fire safety, I would say. That's a good way of putting it.
Yeah, that's, I mean, my colleague Joe is having his presentation on how regulations regarding fire are actually informed by catastrophes. So there's a very nice graph indicating major catastrophes such as Grenfell, and then how this had led to changes in the regulations and the relevant guidelines. So for example, even the project, the SAFE project was due to the funding from the government due to the big catastrophe that happened in 2017. So
right.
It makes sense. Also in other engineering principles, this is how research is driven by catastrophes, unfortunately. But I mean, I totally agree with you. We can try and be more proactive. But
I was alluding into that. How could we, all of these, help us to basically inform this data into policies? How we can actually realize them into policies for the respective, I guess, governments? Because it seems that we're a bit disengaged, like in terms of like what we want, because there says we're doing and the policies that are in place. There's a bit of a discrepancy in terms of the years. Like a lot of the things that we see in the codes are from the requirements are from the 70s, or even before or
this is
80s.
also reflected on the choice of the fire loads that we use. I mean, especially in your case, if you have combustible components on the walls, I mean, most of the codes nowadays only take into account, a floor distribution of the fire, which is not the case anymore. And it shouldn't be the case because now we've moved on that. So, but still there is a lot of work to be done to implement this new concept into the design phase.
Right. Yeah, indeed. I think, sorry, I won't take all the time. There's another question there from Dr. Akhtar Hossein.
Three phases are interacted and so this is a numerical code. This is an open source code called Fire Dynamics Simulator. It's able to simulate combustion. Now there is a possibility to simulate solid particles if needs to be, and also there is a possibility to treat liquids and how they evaporate and everything. So it's an open source safety software from the National Institute of Standard Technology, and those type of actually it's a safety software specifically tailor-made for fires. So with it can be used very accurately for fires with low velocities, such as a fire. So actually, you can accurately predict how, for example, a sprinkler would suppress fire and the relevant differences in the state of the gases are implemented. Now, I'm not sure if I totally understand your question. I hope I was able to answer it. However, there's another, Konstantinos.
Yeah, we got another question. It's related to timber and regulation.
However, unfortunately, it's not always the case. Based on this, do we have enough knowledge how we studied probably the use of timber in tall buildings? Timber is used in many countries, but do we actually know the dynamics when timber is involved? Actually, this is a very good question, and actually this makes sense. And actually, this is hopefully the drive that many people at Queensland universities do what they do at the moment, because we need more information on how timber and charring and fire propagation, and actually how we can implement coatings and different substances to protect timber, but leave it exposed also. So I'm not sure that the solution is to encapsulate timber, or can we use some treatment or engineering timber to actually improve to actually understand how it will react under fire conditions. So actually, wood in my mind is one of the most resilient materials with a lot of very positive attributes that can contribute to both greener buildings, but also, if used correctly, used in safe buildings. So I think that what you highlight, more research to be done in this field, is something that I would agree with you. And I'm not sure if Stavros can discuss something more, since it's his research field per se. So feel free to comment if you want.
I'm just trying to see because there's
Yeah.
another question, but I can follow up on that if we have time.
It would be hard to know every single aspect.
That's it.
I mean, yeah, that's would you recommend any major component we should be very familiar with? Now, this is a major field, okay, and it takes many years and a lot of experience in order to be or to feel competent. So actually, first of all, don't get very stressed. If and when you join a company, you will be trained and guided, and there are frameworks that we follow. And in my mind, the best thing that a young professional should do is continuous professional development. So if you stay up to date, if you try and follow what is happening, if you are participating in training event, that can be a very useful procedure. Now, depending on the specific area that you will concentrate, you will have to educate yourself and be proactive, and try and discuss with colleagues and try and participate in events. And actually, if you are registered in a professional body, try and participate in in the relevant activities organized by those. So one of my advices would actually be registered in a professional body, try to be up to date, try to do CPD for example, conversations as we have today, see what other people are doing, and actually try and implement best practices into your everyday design.
Follow up on that question about the numerical model.
Liquid phase. So liquid gas phase interaction there is, and also there is an interaction with the solids. So in this software, you can implement solids with specific thermal properties. So you do have heat transfer being resolved. And then on top of that, there is the interaction between liquid and gas phase, especially and there are many different models implemented in FTS. Also in terms of turbulence, there is a lot of different turbulence models that can be used. Also, there is a model for the liquid movement. So in that sense, I guess it is a three-phase interaction. So, and also this is an open source code. It's not developed by our team per se, but we do use it as plan of our numerical analysis by implementing the relevant input to be resolved, such as, for example, in this case, the geometrical features, all the materials that and the thermal properties that were included, the fuel properties, combustion, how the fuel was evaporated, the relevant boundary conditions, and many other parameters. So hope that's more clear now.
I think we're done. If there's any more questions, we're already like 7.
Yeah, we just finished right on time as we planned.
Thank you. It's been very nice to be with you, even virtually. Hopefully we get the opportunity to meet in the near future.
Yeah,
and I would be very
definitely.
happy to discuss with you at any time.
Yeah.
And
right.
Hope that was useful for everyone. And sorry for the high speed of my, I did talk rather quickly, so apologies for that.
No, it was all good. I just want to add to what Con was asking just now about timber. I just want to quote Jose Torero. I was reading one of his interviews recently, and he said timber can be perfectly safe if it's done right. This is not a technological or technical problem. It is fundamentally a problem of competency. And said timber is it's perfectly safe if done right. But but also he went and said that the ultimate consequence in the case of a timber building can be much more significant than obviously in the case of a concrete or steel building. And the issue here is that we don't have guidelines on how mass timber buildings, competent guidelines on how mass timber buildings should be constructed, and we end up going for the safe solution of encapsulating the whole building, and then we call it mass timber building. Now, but there are now a bunch of us are starting to investigate alternative ways. As part of my research, we're looking into application of intermeshed coatings, which they've been around for a long time for steel. They are a bit promising in reducing the charring rate, the char depth, but this is only the beginning. There are other things that need to be considered, such as the connections, where you have the integration of steel with timber. When you have different orientations when you're testing how the timber is going to behave in a ceiling configuration versus if it's a wall or if it's a column. And there are some good actually research happening from David Barber and Panos Kotsovinos from Arab in Europe. There is a lot of good work happening around to inform people on that aspect. But at the moment, at least in Australia, and I'm sure probably in Europe as well, there's no really guideline in how we go about doing that. There is a bit more work on the aspect happening in the US and Canada, but talking with David Barber, who was the fire safety engineer in, I can't remember, was the Ascent building in, I can't remember, one of the Ascent Tower in the United States, one of the world's tallest mass timber buildings. There's a bit of a lack of experience, and when we talk about timber buildings, because people think about it from a structural point of view, in the cold case sense, but they don't take into account the fire, and sometimes there's a bit of misconception about burning of timber or charring. You hear architects saying it doesn't burn, timber doesn't burn, it chars, and therefore insulates itself. And these are they should be prosecuted with when they use this kind of wording. But anyway, yeah, there is a lot of good work happening, but nothing in play at the moment. But I think there are very knowledgeable people in the likes of Jose, David, and others who do excellent work in that area. And if consulted, I think we can still design them in a safe way.
Certainly.
Yeah.
Great. Thank you so much, everyone.
Thank you. Once again, thanks for your time and you willing to share all your research and your experience with us. Yeah, I guess we just going to end this session. Thank you once again.
Bye-bye. Thank you all, and thank you for your questions.
Thank you, everyone. Have a good weekend.
Bye-bye.